I will tell you what this is all about. So I'll go over what we covered last time, which was basically just the polynomials. Just really quickly tell you what it's all about again. And then we'll talk about quadrature rules, because I don't know if you noticed, but in order to evaluate the coefficients of these polynomial expansions, you need to do that dot product, and that dot product is basically an integration. So we're going to have to talk about quadrature rules in one dimension whenever your input is one-dimensional, and expand these quadrature rules to multiple dimensions. In quadrature rules in multiple dimensions, they're known as cubatures. And we're going to introduce sparse grids in order to be able to go to more than one stochastic variable. And whatever we're going to say will work for problems with, let's say, moderate dimension up to 10 or 20, or even a little bit higher if things are nice and smooth. And then we're going to use whatever we have, these quadrature rules to solve actual problems. In particular, we're going to propagate uncertainties through a dynamical system. Whatever I showed you last time, I hope we're going to have a little bit of time to go to go and basically derive all the equations that you need to use. All right, so the orthogonal polynomials. So orthogonal polynomials with an input that is just one scalar. They are, of course, polynomials that look like that. And we said that we define these polynomials as an orthonormal basis on the space of square integrable functions. So any function, so we consider basically the space of square integrable functions, and in that space we create a basis that is basically consisting of polynomials, and these polynomials are pairwise orthogonal. Okay, if you integrate one with the other using the right weight factor right there, which is the underlying probability density of whatever is random in your problem, should be 0. And of course, when you calculate their norm, you should get 1. And we said that this space is a Hilbert space. It's a Hilbert space because it's a vector space with an inner product or a dot product. And on top of that, it's also complete, meaning that every sequence that looks like it converges, it does converge to a function inside that space. And the idea is that your model, whatever that is one function inside that space. And if you have this basis, then you have a guarantee that that function can be expanded in that basis. That's pretty much it. So to propagate uncertainties with polynomial chaos, you basically need to construct this basis and then go take your model and expand it in that basis, and then certain statistics come automatic. And we discussed, we talked about constructing these polynomials, and we said that you can start with any set of linearly independent polynomials, and then you can apply to that set the Gram-Schmidt orthogonalization procedure. But there are better ways of doing that, and this is what the orthpol algorithm do. And I give you some examples of these polynomials. For example, in when the underlying density is uniform from -1 to 1, you get the Legendre polynomials, which look like that. That's pretty much it, okay? And then to go to higher dimensions, what you do, I mean, you can do the same thing. Polynomials in higher dimensions look like that, okay? So you have all the components of x raised to a power multiplying each other with some coefficient. Again, the definition of the orthogonal polynomials is pretty much the same, but the integral is a multidimensional integral. That's the only difference. Apart from that, you still have a dot product or an inner product. The polynomials have to be orthogonal, so on and so forth. This space now from RD to R is also a Hilbert space, etc., etc. And you could construct these polynomials using the Gram-Schmidt orthogonalization procedure if you have a set of linearly independent polynomials, but in practice, it is next to impossible to do that. So most of the times sometimes when your random variables are independent, so when you have a set of random variables and each one of them is basically completely independent of everything else, then their joint density factorizes like that, and you can build orthogonal polynomials for each one of the components and then put them together, basically taking all combinations of these polynomials and multiply them together. Okay, so this is known as the tensor product of the D sets of polynomials that you have in there. And this may look very restrictive, the assumption that whatever is uncertain in your model can be decomposed in a set of random variables that are independent, but it is actually true every single time. You can actually do it, at least in principle. In principle, it is always possible, no matter how complicated your stochasticity is, it is always possible to describe it with a set of independent random variables. But we're not gonna get into that. All right, so what is the relation to uncertain propagation? Why do we do all that? Well, in the uncertain propagation problems, we have a random variable that is a random vector, for example, with a known density p of x, and we have a model f of x that is a quantity of interest, and we are assuming that this model is basically square integrable so that it is inside this Hilbert space. And if it is inside this Hilbert space, then it can be expanded in a basis of polynomials. Okay, that's the whole point. And these coefficients here, as soon as you can find them somehow, then you can calculate all sorts of statistics for your model. First of all, you have found a representation of your model that is very cheap to evaluate. So imagine that your model could require the solution of a differential equation or a partial differential equation or something, or even doing an experiment, an actual experiment, and now you just have expanded it in polynomial basis. So you can evaluate it anywhere you want as soon as the coefficients are accurate. And in particular, if you want to propagate uncertainty through it, the uncertainty of x propagated through your model, you can do it very fast. For example, the mean is basically just the first coefficient, and the variance is the sum of all the coefficients except the first one squared. Okay? The sum of the squares of all the coefficients except the first one. And of course, you can derive formulas for any of the statistics you want, but you could also just use plain old Monte Carlo on this expansion. So we're going to concentrate on how we find these coefficients. Okay, and one of the basic things that we need to find these coefficients is doing these integrals. Okay, so let's see how we can do these integrals. It's all about quadrature rules today. And quadrature rules look like that. So let's introduce a quadrature rule for a simple integral integrating f of x from a to b, and there is no density there, or the density is the uniform density, if you like. So it's just this, all right? Now, a quadrature rule is basically an approximation of that integral of this form. Some weights times the value of the function at some points, sum over all these points. Okay, that's pretty much it. This is called the functional of f. But anyway, it's really just that. This is any quadrature rule can be described like that. So you see that you need some weights. These wk's are the weights. These xk's are called the nodes of the quadrature. And what you have to do is you have to go and evaluate your model at these points, multiply by the corresponding weight, sum over all the possible nodes. The number of nodes is n. Okay? And let's see, there are a lot of choices for quadrature rules. So actually, before I show you these, let me show you some very intuitive quadrature rules, which I'm going to have to do by hand. So let's go here. Okay, I'll show you a very simple quadrature rule. So here is x okay, your y-axis, and let's say we have a function like that. I'll show you a ridiculous quadrature rule. Say this is A, this is B. Okay, here's a ridiculous quadrature rule. The quadrature rule says, it's called the midpoint quadrature rule. It says evaluate, it has just one node, and that node is basically the middle point of A and B, so it is A plus B divided by 2, and you go there at that middle point and you evaluate the function. Okay, so this right here is f of x1, f at the middle point. Okay, and then you basically approximate the integral with which is the area below the black curve, with the area of this box. Okay, so this midpoint quadrature rule is basically b minus a. This is the weight f evaluated at a plus b divided by 2. Okay, so this is the simplest quadrature rule that you can come up with. It's a ridiculous quadrature rule, obviously. It only works if a and b are very close together and your function doesn't really do anything in between, and you can approximate it like a constant. I'll give you another quadrature rule. It's really as simple as that. Another quadrature rule is the trapezoid quadrature rule. Again, here's our x, here's our y, here's our a and our b, here's the function. Okay, the trapezoid quadrature rule has two nodes. One node is a, the other node is b. You go and you evaluate the function here and you evaluate the function there, and then you approximate the function as a line, and the area below the red line approximates the area below the black line. Okay, so that quadrature rule f, it's the trapezoid quadrature rule, is basically, do you remember the formula for the area of the trapezoid? Small base, right? Oh god, I don't remember it. Anyway, okay. It's W1 FA plus W2 FB. I would have to waste 2 minutes to derive it, okay, it's not a big deal. But you could do it. But it can still be written like that, and you have a W1 and a W2. Okay, and you can, and let me show you a more complicated quadrature rule. It's called the Newton-Cotes rule, which is a generalization of this idea. You should not really use it, let me just say it from the beginning, because it doesn't really work, and I will show you why it doesn't work. But the idea is to take AB and pick nodes that are equidistant. Right, so you take AB and you divide it into n plus 1 segments, and each edge point of these segments is a node. Okay, so here are your nodes. Your nodes are A plus HK, where H is this. Okay, the size of these guys. And then you evaluate your function on all these points, and you approximate the function itself with a polynomial. Okay, you just approximate with a polynomial, but a special polynomial, an interpolating polynomial, which is called the Lagrange interpolating polynomial. Do you remember that from your analysis class? So whenever somebody gives you observations of x and y in one dimension, it is always possible to construct a polynomial that goes through them. Okay, if you increase take a sufficiently large degree. If you go to degree n minus 1, you are going to capture, to create a polynomial that goes over through all these points. So it's not really a big deal. So you take your, let me draw it. Let's do it. So the idea is to take your function a, it's from A to B, here's your function, all right. You pick equidistant points. Let's pick 1, 2, 3, 4, 5 points. At each one of these points, you evaluate the function, okay. And since you have 5 points, it is possible to pass a polynomial of degree 4 through all of them. Okay, and there is a formula that gives you exactly how this polynomial looks like. It's called the Lagrange interpolating polynomial. And then you can draw this polynomial. Here you go, it's going to be like that, whatever. Okay, you know what happens to polynomials far away from these points? They go to hell. Okay, they go to infinity or minus infinity, always. So, you know, you'll get things like this, things like that, far away from these points. This is what happens. But anyway, and then the idea is to approximate the area below the black curve using the area below the magenta curve. Okay, so you just integrate the polynomial instead of the function, and because it is possible to get the polynomial coefficients exactly for these Lagrange polynomials, you can do this integral exactly. Okay, so here's how the quadrature rule is constructed. You approximate the polynomial using the Lagrange interpolating polynomial, which happens to have this form. It's basically the value of your function times a special polynomial called the Lagrange polynomial. It doesn't really matter what it is, but you can Google it and find it. Okay, you have seen it somewhere in your life, I'm 100% sure. You just don't remember it. And then you take this expression and you integrate over x, and you see that, you know, these coefficients are going to pop out, and then this, you need to do this integral, but this is a known polynomial now, so you can actually do this integral analytically, and this is what gives you the weights of your quadrature. Okay, and let's see how this thing works in practice. So here we go. We have the function that I want to integrate is basically the blue function, and the integral is the shaded blue area. Okay, so the blue function is what I want to integrate from -1 to 1, and I'm using the Newton-Cotes rule of order 3. So this means that I pick 3 equidistant points, this, and this. I evaluate the function, the right function at these points. These are the green dots. Then I fit the Lagrange, I take the Lagrange polynomial. Lagrange polynomial is the orange line, and I'm going to approximate the blue shaded area with the orange shaded area. That's all, okay? And if you increase the number of nodes, you can go to 5 nodes, so 1, 2, 3, 4, 5. Again, you fit a Lagrange polynomial of degree up to 4, and you approximate the shaded blue area with the shaded orange area. And you could go to degree 10 and you nail it, okay? So you have 10 green points on each one of them. You evaluate the function, you interpolate using the Lagrange interpolated polynomial, and you can find it, okay? Make sense? All right, but it doesn't work, except from this case, okay? So in general, it doesn't work. It can get really, really ugly. So I just pick a really bad example of this, which is a step function. So imagine that you want to integrate a step function. It's a pretty simple function, okay? But look at what happens. Degree 2, fine. You are approximating the step function with the area of this triangle. Forget about the fact that this triangle actually has the correct area, okay? You don't really know that before because the blue line is not visual to you. It's just an accident, okay? And let's say that you start adding more points. So you add 1, 2, 3, 4, okay? And this is the polynomial approximation to the step function. And then you add more, and you see what's going to happen. The polynomials are not going to behave nicely. So here, look at that and that when you go to degree 8 to 8 points. I would double it and go to 16 points, but what I get is ridiculous, so I put an intermediate step. I added 10 nodes, and you see that this region becomes very big, and this region becomes very big, and then you're approximating the blue shaded area with the area below the purple line. And this is what happens when you go to 16. So basically you don't see anything because the polynomial is behaving really, really It's really nasty at the edges. Okay? It just doesn't work. It just doesn't work. And I have in the handout an example that you can play with and see why it doesn't work. Does anybody know how is this phenomenon called? Gibbs phenomenon? Gibbs phenomenon. Is there another name? All right. So let's try to fix that. And the way to fix it is to go to Gaussian quadrature. And I'll tell you what Gaussian quadrature is. It is basically just like the quadrature we had before, but the nodes, the selection of the nodes is special. You don't pick equidistant nodes anymore, you pick special nodes. Okay? And what is so special about these nodes? This is what is so special about these nodes. They are the roots of the orthogonal polynomial of order n. This is what they are. So if you want to construct the Gaussian nodes, what you do is you take your, let's say we are from -1 to 1 with a p of x equals to 1. So we have the Legendre polynomials. Okay, we want to integrate something with a uniform weight. So what we do is we construct the orthogonal polynomials. We go to the nth one and we ask it, what are your roots? Okay, where do you get 0? And this is what gives us our nodes. And of course there are a bunch of theorems that I haven't really told you about, like for example that the orthogonal polynomials that we constructed have real roots. So the nth orthogonal polynomial has actually, the degree n orthogonal polynomial has n real roots, okay? And that these roots can be found by solving a very simple eigenvalue problem. But forget about that because it would really take us 3 weeks of polynomial chaos to do that, and it doesn't really matter. But this is the only difference in the Gaussian quadrature is this, the selection of the nodes, nothing else. Everything else is just like the Newton-Cotes rule. You build the Lagrange interpolant and you integrate that, okay? Now, there are 2 theorems for Gaussian quadratures that are extremely important. Theorem number 1, this procedure, this quadrature rule, interpolates exactly polynomials of order 2n plus 1. So even though it is based on a polynomial that is of order n, it can approximate the integral of 2n plus 1 degree polynomials exactly. So if your model is of degree is a polynomial of degree 2n plus 1 or smaller degree, you will get an exact answer for the integral. This is one theorem that we're not going to prove, but I'm just going to state. And it's a little bit strange, right? Because you're using endpoints and you're getting 2n plus 1 accuracy. And the other theorem is that there's no other quadrature rule with the same number of points that does better, which is a pretty good deal. Okay, so you know that you have the optimal quadrature rule for integrating polynomials. That's the catch. So this doesn't mean that it's going to be better than any other quadrature rule for an arbitrary function. It just means that if your function is in the class of polynomials, there's no better thing to do. So if your function is smooth, let's say, then this is pretty close to universal optimality. All right, so here's how it looks like. So you see, instead of equidistant nodes, so here we have Gaussian quadrature of degree n with of degree 3 with 3 nodes. So we have 1, 2, 3 nodes. Notice that these nodes are not equidistant. If they were equidistant, you will have 1 here and 1 there. These are the zeros of the degree 3 polynomial, degree 3 Legendre polynomial. This is what they are. So we interpolate, we get the Lagrange interpolant, and then we approximate the blue area with a orange area. But again, I mean, this is what worked before, and it continues to work now. Just notice that the nodes are not equidistant. That's the only thing I want you to notice. Anyway, and it does behave better in things like step functions, but not that better, but better. Okay, so I'm increasing the degree, the number of nodes to 8 to 16. So you see that the Gibbs effect has been tamed a little bit, but it's still there, but it will occur later on. Okay, but it is tamed considerably. Okay, step functions are actually very hard functions to build polynomial approximations of. But anyway, okay. Now, so it does behave better, but there is a major problem with Gaussian quadrature, and that is that it is not nested. That means that the nodes you get for degree n are not included in the quadrature of degree n plus 1. This is the problem, right? So you build an approximation for degree for n equals 3, and then you go to n equals 4, and you have to evaluate your function at 4 new points, and you cannot reuse any of the previous function evaluations. You go to degree 5, and then you have to evaluate your function at 5 new points, and you cannot reuse any of the previous points. And this is a major problem if your function is expensive. So ideally you would like a quadrature rule that that is nested in the following sense. You build it for n nodes, you get an approximation, then you go to n plus 1 nodes, and you get another approximation, but you actually reuse all the data. So you only have to evaluate your function at 1 new point, let's say, okay? And you update it and you compare the results until you converge, okay? So this is the kind of rule we're looking for. Just to highlight that the Gaussian quadrature rule is not nested. Here you see the green points are the 32 degree Gaussian quadrature, and the red points are the 31 degree Gaussian quadrature. So if you build the 31 degree, you're using the red points, and you have to evaluate your function or your model at the red points. And then when you go to 32, you have to evaluate your model at a set of completely new points. Okay? And this is not good, because you would like to reuse the information you have on the red nodes. All right, so to overcome this difficulty, I mean, obviously what we really want is a set of rules, quadrature rules that are nested. And the most famous nested rule is the Clensor-Curtis quadrature rule. And I'll just guide you through the derivation without really doing it, okay? I'll just show you how it works. So you want to get this integral, and you transform that integral like that. So you say, I'm going to, instead of integrating over x, x is between -1 and 1, so I can say that x is the cosine of an angle. Okay, so I can do this transformation and write this integral like that, so this is exact. Okay, there's a different way of writing this integral. And then you can take this thing here and you can expand it in a cosine series, in a series of cosines. This is also just a Fourier transform basically of f, that's all it is. And then the coefficients are given by that. So this actually uses on the background another Hilbert space, or actually just uses a different basis for the same Hilbert space. That's all it does. So the coefficients are given by that. And then if you knew the coefficients, then the integral would be this. Okay? And now there is a theorem from signal processing which is called the Nyquist-Shannon sampling theorem that actually allows you to find these coefficients exactly. So these coefficients ak, if you're using n points, n evaluations of the function, you can find them exactly. You can find the ak's for k less than the number of nodes you're using exactly. And this is the formula. Now again, you can look this up. This is probably something you haven't seen unless you have taken a course in signal processing, but it's pretty well-known formula. And this formula basically looks like a quadrature rule, okay? And the quadrature nodes are these points right here. So basically the nodes are the cosines of JP over red. And these are equidistant in the theta space, but they're not equidistant in the x space. And then if you take this and you combine it with this formula and rearrange, you can actually see the quadrature rule. You can see the weights multiplied by function values. Okay? But anyway, I'll show you how this thing works. But before, let me just mention two theorems. First, the Clenshaw-Curtis rule is nested, but it's not nested if you go from n to n plus 1. If you go from n to n plus 1, you actually get a completely different point. But if you go from n to 2n, the 2n rule contains all the endpoints and all the points in between. Okay? So now with the Clenshaw-Curtis rule, you can start with 2, then go to 4, then go to 8, go to 16, go to 32, and in between, and as you go along this sequence, you're going to be reusing the function evaluations along the way. So this is theorem number 1. Theorem number 2, the Clenshaw-Curtis rule integrates polynomials of degree n plus 1 exactly. Okay, so it's not better than the Gaussian quadrature, but it's a price you are probably willing to pay if your function is expensive and you want to reuse its values. And at the end of the day, this exactness guarantees are only concern polynomials. So if whatever you're integrating is not a polynomial, it doesn't really matter that Gauss quadrature is better for polynomials. If you don't have a polynomial, right, why would you care? Anyway, so from now on, we will only use the Clenshaw-Curtis quadrature, and the reason why is basically because it's nested. Okay, that's the reason why. So here's how the Clenshaw quadrature points look like. And what do I have here? Confuse myself. So degree 2 are the, anyway, you'll see how this figure is created in the handout, and you probably understand. But I probably go up to degree 16 or so. I go to something like 2, 4, 8, 16. And then I show you all the points with different colors, which I don't remember what they mean, so let's just move on. Okay. So what I want to show, what I really want to show you is how to use these rules to do actual integrals. So the handout, that's what I'm doing, and one of the examples I'm using is basically validating the orthogonal polynomials that we constructed, right? So I'm asking the question, if you compute the dot product of phi I with phi j for the Legendre polynomials, let's say, do you get the Kronecker delta? Do you get 0 if I is different than j, and 1 if I is equal to j? So, you know, this is the inner product that I want to calculate. It's just an integral. So I can use the Clenshaw-Curtis rule to evaluate it. This is what the Clenshaw-Curtis rule tells me. It tells me here are your WKs, but the Clenshaw-Curtis rule was developed for a weight function that was equal to 1. Okay, but here I have 1 over 2. Okay, so I have to divide by 2. That's not a big deal. And the one polynomial evaluated at the node, the other polynomial evaluated at the node, sum of all the possible nodes. And what you see here, when I have the code, you know, that does that, and how you get the CC rule, the nodes, and how you can actually put it all together, and you see that to at least third digit, the accuracy is quite good, right? So the first polynomial with the first gives me 1, the first with the second gives me 0, and so on and so forth. Okay. Questions? Am I going too fast? No. Okay. It's actually easy. This one, it's one of these ones, until it becomes hard. Hang on. Okay. All right. So the CC rule only works with polynomials with integrals that look like that. Okay. So minus 1 to 1 f of x dx. But what we really want to be doing are expectations that look like that. So you have an x with a probability density p of x, or with finite or infinite support, and you want to do an integral like that. Okay, or perhaps here you can put your polynomials or whatever. Okay, so how do you go from a quadrature rule that is designed for this integral to a quadrature rule that works for this integral? It's actually quite easy. You just have to transform the integral. Okay, so here's the transformation. There's no one way to do it. You can do it many different ways, but this is the transformation that I propose. So you define another integrand, z, which is 2 times the cumulative density function of your random variable minus 1. The CDF of your random variable, if you put in there your random variable, it's going to give you a number from 0 to 1. Okay, so f of x, where f, capital F, is the CDF, it's a probability, so it's a number between 0 and 1. So this transformation takes basically x, which could be from minus infinity to plus infinity, and it maps it from minus 1 to 1. Okay, so you now have mapped it from minus 1 to 1, fine. You can find the inverse map, it's like that. So x is basically the inverse CDF of z plus 1 divided by 2, big deal. You can find the differential, dz is going to be 2 times the derivative of the CDF times dx, but the derivative of the CDF is just the probability density. So you get 2 times px dx. Okay, and then you compare these. You apply the transformation here. So you see here you have px dx, 2 times px dx is dz. So this is going to be 1 over 2 times dz. And here you just replace, and this is what you get. Okay, so that if you transform the integral, you will get this. So it's basically the function that you're integrating evaluated at the node is basically now it's going to be a transformation of the CC nodes of this form. Yeah, I think it's pretty straightforward. Okay, so this thing here will become dz divided by 2, and this is f minus 1, z plus 1 divided by 2. And then this will become minus 1, this will become plus 1. I hope you remember how to transform integrals, because that's pretty much all I'm doing. Okay? Anyway, so basically we have shown that if you have the CC rule here, you can use it to evaluate this integral by to derive a quadrature rule for this integral, but the weights of the quadrature rule should be basically 1/2 the weights of the CC rule, and the quadrature nodes should be the quadrature nodes of the CC rule pass through the inverse CDF. Okay, so this will take nodes that are from minus 1 to 1, and it will actually spread them from minus infinity to plus infinity. That's all that's going to happen. Okay. All right, and let's use this idea to validate the Hermite polynomials, which are the polynomials that are orthogonal with respect to a Gaussian. Okay. So the integrals that I want to calculate are phi phi j times the probability density of the Gaussian. Okay, so this is my p of x, probability density of the Gaussian. And if I have a quadrature rule for minus 1 to 1, then I transform it based on what I gave you before to a quadrature rule from minus infinity to infinity, and I'm going to be using the CDF of the standard normal, which is typically called capital phi. Okay. So you see that the integral can be approximated like this. Okay, so the nodes are these. This is pretty much it. And the accuracy is again quite good. Questions? All right. Now that we know how to integrate in 1D, let's integrate in higher D. Okay? So, if you have a one-dimensional quadrature rule, actually zoom like that. If you have a one-dimensional quadrature rule, it looks like that. So that evaluates a one-dimensional integral. You can create a two-dimensional quadrature rule by taking what is known as the tensor product of the two quadrature rules. So I'll show you how this thing looks like. Formally, the tensor product between two quadrature rules in one dimension is a quadrature rule in two dimensions, and that quadrature rule is this quadrature rule. So it's a quadrature rule whose nodes are the nodes, all pairwise combinations of the nodes of the 1D rule, xi, xj, where xi and xj are nodes in the 1D rule, and the weights are all the pairwise products of the 1D rules. So this is the definition of the tensor product of the quadrature rule. Just to give you an idea of how the nodes of the tensor product of a quadrature rule looks like, I have taken the CC rule in 1D. So if you just take one slice here, you see the CC rule in 1D, okay? And I've taken the tensor product of that rule with itself to create a two-dimensional quadrature rule, and the nodes of the two-dimensional quadrature rule are all these points, okay? That's pretty much it. And you can do that also in 3 dimensions and in 4 dimensions, 6 dimensions. At some point, you're going to run out of memory in your computer. Okay? And that point is very, very, very soon. Perhaps dimension number 4 is as far as you can go, depending on how many quadrature points you're using. All right? So, even though it is very intuitive to understand this rule, it is actually completely useless. Unless you are in 2 dimensions, then perhaps it is useful. Okay? But for more than 2 dimensions, I would not recommend it, because the number of nodes in it grows exponentially with the dimensionality of the space. So if you have n points in a 1D rule and you go to d dimensions, you're going to get n to the power of d nodes, okay, which is ridiculous. Let me just motivate sparse grids like that. So you want to be able to construct quadrature rules in higher dimensions, but you don't want all these points. Okay, obviously the problem is that you have too many nodes. So you're saying, okay, let me just get rid of a lot of these points, right? So you're basically saying, can I construct a rule that perhaps gets rid of pretty much everything here, here, and here? I don't want all that. Okay, can I just construct a rule that, throws away the vast majority of these points? And yes, there is such a rule, and it's called the Smoliak quadrature. Okay, and it's a little bit hard to understand what the formula does, but I think I can explain what it does visually. Okay, so first, how does that work? So you can create a Smoliak quadrature by taking any set of one-dimensional quadrature rules. Actually, you could let's say by taking a single one-dimensional quadrature rule, and we're going to use tensor products to create higher dimensional quadrature rules, but we're going to be throwing away some of the nodes. Okay, so first of all, you need a one-dimensional quadrature rule, but there is one requirement: it has to be nested. Okay, This is the one requirement. So if you double, let's say, the nodes of the quadrature rule, it must be the new nodes must include all the old nodes and all the add nodes. Anyway, to define the small quadrature, all you need really is tensor products, and that's a formula. And okay, you probably need to meditate with it for like a week to understand it, and perhaps you also need to program it in order to understand it. So I'm not even going to attempt to tell you what it does. All I will pinpoint is that it actually builds a d-dimensional quadrature rule from the d-1 dimensional quadrature rule. So it's basically a recursive definition of quadrature rules in higher dimensions. And it doesn't quite take the tensor product of two lower dimensional quadrature rules, but it takes the tensor product and it throws away some stuff. Okay? And this is how it looks like. So now we start with a one-dimensional quadrature rule that is nested, and everything happens in levels. So this is the first level of the small quadrature rule in 2 dimensions. It's just 1 point. Okay, so the underlying quadrature rule is basically the CC quadrature rule. And I'm going to start increasing the level and introducing more points. Okay, so first at the center. So basically the first level of the small quadrature approximates your function as a constant. Second level adds 4 more points. Okay, so it goes, the underlying one-dimensional quadrature rule go from 1 point to 2 points. Okay. Level 3, you go from 2 to 4 points. Level 4, level 5, level 6, etc. Now I don't know if you noticed that, but if you look carefully, you will start seeing patterns. So whatever nodes you're taking here, so initially you have a big square, and you're taking nodes in that big square. But then you see 4 other squares, and the nodes you're taking in these 4 squares are basically symmetric. I mean, are basically a little image of the nodes that you took in the bigger square. And then you start seeing other squares, and then the nodes you pick inside these squares are also copies, let's say, of the nodes you have taken in the bigger square, and so on and so forth. So basically it's a kind of like a self-replicating map. Okay, so tell me, what is the big deal? Why does it work? Well, I will tell you that it's not always working. Okay, so don't worry about that. But it works. So I tell you first what it does. So it throws away from the tensor product, it throws away all these terms. If you were doing, let's say, Lagrange interpolation with these nodes, you will be basically throwing away all the high order polynomials that involve combinations of x1 and x2. So the highest order, okay, let me just say that. This is what it does. It throws away some of the pairwise combinations of the Lagrange interpolants. And if these are not useful in your problem, then it's going to work fine. If they happen to be useful in your problem, then it's not going to work fine. What else does it do? That's pretty much it. Okay, and the most useful thing about sparse grids is that the number of nodes does not grow exponentially, or at least at the beginning, as the number of dimensions grows. Okay, it grows much slower than the tensor product. Okay, so here you see, I'll show you how the number of nodes in two different tensor product quadrature rules using underlying one-dimensional quadrature rules with different levels grows as the dimensionality of the input space grows. So you see that, I mean, the product rule really explodes very, very, very fast. So it's completely useless, right? So you see for 10 dimensions, you need 10 million nodes. For 20 dimensions, you need 10 to the 13 nodes. But sparse grid, the sparse grid quadrature grows much slower. Okay? So you can actually easily do it for 20 dimensions. For 20 dimensions, you will need 1,000 nodes. Yes?
What is L?
L is the level of the underlying one-dimensional quadrature rule. So the tensor product is built out of taking the tensor product basically of D one-dimensional quadrature rules. How many nodes do you have in that quadrature rule? How many nodes, how many points does the one-dimensional quadrature rule have? For L equals 1, it has one node, I think, not one, more than one. It has, let's say, so this L, I don't remember it exactly, but what I do remember is that the L specifies the number of nodes in the one-dimensional rule, and that number of nodes is basically some number proportional to L, which could be basically, which could just be L, okay, but I'm just not sure if there is a constant there. So for this one, let's say that this L is, let's say that it is 2. So here this means that the original quadrature rule is built with 2 points, and here the original quadrature rule is built with 4 points. This is the difference. So the number of points in the 1D quadrature rule is 2 times L. I think this is accurate.
Yeah, what does L equal 1 mean?
What was that?
L equals 1. What's the difference between 1 and 2?
So the difference between L equals 1 and L equals 2 is the underlying one-dimensional quadrature rule. For L equals 1, the underlying quadrature rule has 2 nodes. For L equals 2, it has 4 nodes. For L equals 3, it's going to have 8 nodes. And then you take tensor products of these. This is the difference.
Even in the before slide, what is max level?
So max level here is that L. How many nodes do I use? So, okay, this I haven't explained it very well, so thank you. So this is L, okay, and that L specifies the number of nodes in the one-dimensional quadrature rule, which is probably 2 times L. Okay, so how many units do you use in order to build this thing? So yes.
Like this graph I can understand, but why do we need to do it from max level 1 to 6? Like
So here,
the before graphs,
well, because I'm gradually increasing the level.
like what is the concept of
The level, okay, so here's how it goes. Level 1 is just 1 point, okay? So actually the number of, so the quadrature rule I'm using for level 1 is a quadrature rule with 1 point, okay? And that 1 point, you take the you use the smaller formula to get the quadrature rule for 2 dimensions, which also happens to be just 1 point. You can't get any more than that. Now for level 2, you go to 3 points. 1, 2, 3. Okay? And then you use this as the basic unit to build the smaller grid. Okay? And then you see that for level 2, the blue one is going to be in there. This is the level 1 rule, so I keep it there as level 1 rule, and I just add the new points. And then when I go to level 3, the basic unit has also these 2 additional points. And it also keeps all the rest, okay, but it has 2 more points. And then these 2 more points contribute the other green points. And these are the new points that are added on level 3, and you can still see level 2 and level 1. So it's just a way to order the quadrature rule.
So at what level to stop is like how complicated is the function?
Yes. Yes.
So the number of points is not the number of nodes.
The number of points in what?
N.
So the number of nodes, you see it here, okay? But there are the number of nodes of the sparse grid and the number of nodes of the underlying one-dimensional quadrature rule that was used to make the sparse grid. So here you see that we have 1, 2, 3, 4, 5 nodes for the one-dimensional rule, which are combined to give rise to all these nodes for the sparse grid.
So when L equals 1, there is only 1 point.
Yes.
But then as the dimension grows, there is still 1 point.
Level 1. So the level is just a way to order the quadrature rule, okay?
But when L equals 1, no matter what the dimension is, you have 1 point.
I have 1 point in what?
1 point in the space.
I think he is talking about the plot, this plot, because if L equals 1, you really just have 1 point. No matter how the dimension grow, it just always just 1 point. So this curve will not go somewhere.
I'm going to have to look exactly how I created this plot. So this could, the question is this 1 or is it like 2? I'm not sure.
Just like you said, like 1 multiply n is an integer, something like that. The n is unknown now.
Okay, so here's how we're going to fix this, because I do not really remember. L1, L2, L1, L2. Okay, and L1 is smaller than L2. Fine? Good. And you can go to the code in the handout and figure out exactly what I used. I used 1, I used 2, I don't remember, okay? So this is the problem with these lectures now, because I'm making them the day before, and it takes me more than a day. It's 100%, there is a 100% chance there is something wrong, okay? 100% chance. But we'll figure it out. Next time I teach the course, they're not going to be there. But anyway, just keep that in mind, all right? But let me just make this point. So the levels are just used to basically count the number of nodes, okay? This is pretty much it. So if you go to level 3, max sparse grid, you still have in there the level 1 nodes, you have in there the level 2 nodes, oops, you have the level 2 nodes, and you have just introduced the level 3 nodes, okay? If you go to level 4, you still have the level 1, the level 2, the level 3, and you introduce the level 4, okay? And now if you focus here, you will start seeing another square in which you start adding nodes.
So we need to do the convergence check and stop at the level.
Yeah, so the idea is that you evaluate your integrals with level 4, you go to level 5, and you compare the values, and if it hasn't changed, you stop. Okay, and the whole point is that all the points of level 4 are included, in the level 5 quadrature. So the level 5 quadrature only has additional points. Yes?
So like, now when you look at the quadrature points in each of the 4 quadrants, you can see that there's like a big space in there. So like if the function varies in those spaces,
You're screwed. That's what, so you're gonna have to go to a very large level to see it. Okay? This is the whole point.
Then why don't we use something different than going into this process?
This is a very good question. I'm with you. Okay? But this is just what it is. So this is one problem. Like what if something happens here? You're gonna have to go to a very high level to see it. Okay? So one way around it is to create adaptive rules. Rules that basically refine only locally. Okay, but these are very complicated to go over them in this class. So, but they would work as follows. You would start with a big thing, and then you would say, should I adapt? Oh, there's nothing going on here. Okay, so stop working here, but there's something here. So let's focus in here and only increase the level here. And then you split this into small squares and you zoom inside them and so on and so forth. So this would be called adaptive sparse grid quadrature, which is another thing that you could do. But again, you can also fool that. You can fool that, especially in high dimensions. And at the end of the day, there's really nothing better than Monte Carlo in high dimensions. So, and but for moderate dimensions and when the functions are kind of smooth, this works quite well. Okay?
So the weights will also be automatically taken care of.
Yeah. So
When we are doing adaptive thing, what you're saying.
the adaptive thing is very complicated. Okay? It's very complicated. I'm not even going to cover it in class because it would take me at least 2 lectures to do it. And I'm going to have to program it from scratch, which I don't have time to do. But, maybe I'll do it in 2 years. How about that? I'll call you. Okay? So this is my only concern with the adaptive thing, that I don't have code. I have, and it's not easy to implement. All right? But I still don't have time to do it. This is the important thing. The important thing is, how do we use the quadrature rules to propagate uncertainties through dynamical systems? Okay? So let's do that next time. Okay? And let's do it next time. Which is great because now I don't have to prepare another lecture because I'm just going to do that. So let's start with the handout, which is basically gaining experience with the quadrature rules. What are the libraries that you can use to get the quadrature points, how you put everything together with some very simple examples. All right. Now I remind you that there is a new homework set that has been posted, and it is on okay, Monte Carlo. Monte Carlo?
Yes.
Okay. On Monte Carlo. All right. This is due on Friday, but it's not supposed to be hard. Okay. So it's completely doable by Friday. And then we'll give you a homework set over the spring break, but we'll make it due like a week after the spring break. Okay, so even though you're going to have 2 weeks to work on that, and it's going to be on polynomial chaos. Okay, and comparing with Monte Carlo.